me a second here. All right. So 10.9 number 3, I've highlighted it. It says given that the acceleration vector of an object is what you see there, negative 25 cos 5t, comma, negative 25 sine 5t, comma, negative 5t. The initial velocity is v naught equals I plus k. And the initial position vector is r naught is I plus j plus k. Let's compute the complete velocity and position vector. So what you're doing is you're integrating. So let me copy this information down. The original, so this is 10.9 number 3. And I'll change the camera here in a moment. Um, just give me a second to get this all written down. Okay, so I'm going to stop the share and we're just going to work out what these vectors are. Lights here. Sorry for the glare. I can't seem to really avoid that. All right, so maybe I can, that helps just slightly. So you have a vector A of t. Okay, it'll be a little dark. So your vector A of t is what you see there. So you're going to integrate vector A of t. So you just integrate each of the individual parts, and you just have to be careful with your integration. So for example, when you integrate negative 25 cos 5t, the cosine integrates to sine. And because there's a 5 in here, we have to put a 1/5 on the outside. So you should get negative 5 sine 5t. And then similarly here, the sine integrates to negative cosine, which will cancel out this negative. You'll have a 1/5, so you'll have 5 cos 5t. And this is going to be negative 5 over 2t squared. Okay, that's the integration part. But then there's constants. So what I'm going to do is I'm going to write this like a vector. So there's 3 constants, one for each part. So what you do is you plug in 0. Now the sine of 0 is 0. The cosine of 0 is actually 1. So you have 5. And this will be 0. And we're adding the constants A, B, C, and we're trying to get from that what was I plus K, which is 1, 0, 1. And so what we have here is 3 equations. We have 0 plus A is 1. So A is 1. 5 plus B is 0. So B is negative 5. And then 0 plus C is 1. So C is 1. So your velocity vector entirely would come back to the original here. It's going to be negative 5 sine 5t plus 1, 5 cos 5t, take away 5, and then we're going to have negative 5 halves t squared plus 1. Now I'll pause here, and if there's any questions, let me know. You see how I worked in the constants of integration? Um, can you do it with a negative 5t in the argument for the trig function? You can. If there was a negative right here, the cosine absorbs negatives. The negatives and sines come out to the front. So they're only in there temporarily. The original problem that I had didn't have the negatives inside. So just to mention here, in general, just put it off to the side. Cos of negative x is just cos x. So it absorbs negatives. Sine of negative x is just negative sine x, just like that. So you can take care of that instantaneously. All right, so let's finish this off. Let's integrate one more time. And we're going to do this integration one more time. And again, it's good practice to practice your trig integration. Sine integrates to negative cosine. You're going to have a 1/5. So the negatives will cancel. The 1/5 will cancel the 5. So believe it or not, you just get cos 5t. This will be a plus t. And then, of course, we're going to have some more constants. I'll put them at the end. Cos integrates to sine. The 1/5 will take care of that 5. So we'll just have sine of 5t plus, and then that, I'm sorry, minus 5t from this negative 5. Then I have to do this integration. That's going to be negative 5 over 6 t cubed plus t. And I'll just reuse letters A, B, and C again, since why not, right? And I know that when I'm at 0, I plug in my zeros for all of these, and I'm supposed to get this value up here, the 1, 1, 1. So if I plug in 0, cos of 0 is 1. I don't need to write it. Well, actually, I'll write it this way. I have 1 plus 0. Sine of 0 is 0. This is actually just 0. And then 0 here makes that 0. So I have, and then plus A plus B plus C, and that has to equal 1, 1, 1. And so I have 1 plus A equals 1, so that makes A 0. I have 0 plus B is 1, so B is 1. And 0 plus C is 1, so C is 1. So when I'm all done, the the position vector is this function. So I guess A was 0, so I don't need to write anything. And then I have sine of 5t, take away 5t plus 1. That's where this b equals 1 comes in. And then this guy is negative 5, 6 t cubed plus t plus 1. And that would be your complete position vector. And I'll highlight the complete velocity vector. And the common mistake that I see people make when they integrate is that they'll take, for example, I'll scoot this down just slightly. They'll treat these as the constants of integration. They'll just simply stick in a 1, 1, 1 down here, plus 1, plus 1, plus 1. No, you don't do that. What you have to do is you have to actually plug in the t value into the vector value function as it stands right now. These are unknown constants and they have to equal. So this is actually an output. And then you have to just make sure that the A, B, and C are chosen so that what you get here gives you the 1, 1, 1. I mean, you just get real simple arithmetic at that point. Okay. So this was question 10.9, number 3. And are there any questions follow up on this one? Okay. I'll tell you what, I'll give you a moment here to catch your breath. So 10.8, number 4. In fact, while I've got this screen up, I want to discuss with you about the arc length stuff because this is an important thing. So I'll discuss number 4 primarily first, but then I'll go back and actually address some of these earlier questions. I'm going to give you guys a shortcut. So the function for number 4 is RT is cos 8t, sine 8t, negative 4t. And we're doing this at pi over 6, which is 30 degrees. And we want to find the unit tangent, unit normal, and the unit binormal. So we want the big T, big N, and big B. So we'll do that here. With trigonometry, it's not that bad. Big T is just r prime divided by its magnitude, r prime. And so you take the derivative. Let's do that right here. On top, it would be negative 8 sine 8t, 8 cos 8t, negative 4. And on the bottom, we're going to divide by the magnitude. And what I'm going to do is I have to magnitude this thing, but it's not nearly as bad as it looks. So off on the side, I think what I'll do is, let me just do it right here. Magnitude of r prime. Well, if I square this, it's going to be nasty for a moment. Negative 8 cos 8t squared plus 8. Actually, it's a sine, doesn't matter ultimately. And then 8 cos 8t, and then a negative 4 squared. And so you get 64 sine squared 8t plus 64 cos squared 8t, and then you get plus 16. And what happens here is that this is a trig identity. Sine squared plus cos squared is 1, so you just get 64. 64 plus 16 is rad 80. So I'm just going to write that right here. Boom, you're done. That's big T. Okay. Um, you can leave it like that, or you can bring it inside. Doesn't matter. If I bring it inside, it'll look like this. All right, so that's big T. That's the unit tangent. By the way, in our later material, this is going to be a big deal. So memorize big T. Okay. Big N is the derivative of big T divided by its magnitude. Here's the thing. This is actually a unit vector, even though it doesn't look like it. Believe it or not, this thing is a unit vector. Okay. But when you take its derivative, it may not be a unit vector. Oh well. So we're gonna have to go through the process again. The big T's derivative, it's gonna be cos 8t, and so I'm gonna have a negative 64 over rad 80 cos 8t. This will be a negative sine 8t, 64. So negative 64 rad 80 sine 8t. This will be a 0. And then when you take the magnitude of this guy, as nasty as it looks, first of all, that drops out. And you're going to get radical of this will just be cos squared plus sine squared. That'll be a 1. The minuses will go away. So you're going to get 64 over rad 80 underneath the radical. And it's messy looking, but it can be cleaned up. I've got a radical under a radical. That seems kind of peculiar. I guess that's correct. I don't really feel like simplifying those fractions. But and Infinity should accept that if you're careful with your syntax. It doesn't seem like it simplifies quickly. That's part of the problem. Actually, this rad 64 is just 8, so I have 8 over rad 80. Um, Still have a square root of that. I think that's a fourth root. So rad of rad 80. And then when you want to do big B, that's the cross product of T and N. Ugh. So you're gonna have to take the cross product of this and this. Okay. And it should work out just fine as long as you're willing to just be careful with your constants here. This is one of the rare times I might suggest just to use decimal approximations because the cross product, you're going to have a lot of calculations here, but a lot of them will compress down with trig identities. Um, this is for the sake of time. I don't know if this is going to take about 10 or 15 minutes. I'm not going to ask you to do a big B on the test. So this won't be on the test. So big B is not on the test. It's partly because they're usually very difficult to evaluate, you can see that even getting to this stage here, it's going to be a rough cross product. But the more important thing is to just appreciate what you have here. When you're moving along a curve in R3, you get a unit tangent in your direction of movement. You get a unit normal in your direction of turning. That's your acceleration vector, or that's actually a component of acceleration. Your acceleration is usually doing something like that. And then when you take the cross product of these two guys, you get a third vector that kind of sticks up at 90 degrees. And you basically have a traveling frame of reference. These are what are called T and B frames. This is the kind of thing you do on a computer because a computer can punch out these numbers quickly. All right, you do need to know the big T. Big T is important. Make sure you know that. Big N is kind of important. Make sure you know that. Usually, if you can get to big T, you can usually get to big N without too much difficulty. Okay. Obviously, the problem becomes just the algebra. Okay, but I wanted to mention something here. I'm going to go back to the shared screen. Go back to the problems here, especially with the first part of arc length. And I'm going to tell you guys right now, don't waste time trying to work these things out by hand. Okay. For the first one, this should work out reasonably well because it'll be a well-behaved integral because you'll get that sine squared plus cosine squared effect going in again. But look at this guy right here. Look at number 2. All right. I'm going to show you how not to waste a half hour of your life. So this is number 2 on 10.8. The function is 18t, 9t squared, and then we have 9 ln t. And we're doing this between 18, 9, 0, so we just have to infer what that would be. That would be t is 1. And then 36, 36, 9 ln 2, that would be when t is 2. All right, so we're just simply trying to find the arc length of this integral right here. Actually, I looked at the wrong one. No, I'm sorry, I was looking at the right one. 18t. I was looking at number 3. I said number 2. I'm looking at number 3. I'm going to go ahead and just do number 3 since I wrote it down. Okay, so fine, whatever. So, all right, you have to set it up. All right, so arc length is the usually written S, in this case 1 to 2 of mag r prime t dt. Okay, that's the formula for arc length. Let's go ahead and do it. So r prime would be 18, 18t, and then 9 over t. So far, not too bad. Okay. Then you got to take the magnitude of that. You get 18 squared plus 18t quantity squared plus 9 over t quantity squared. And you know what? Stop. In other words, you don't need to simplify this thing anymore. This will actually work out. This will, if you work out the algebra, this will eventually work out to be a perfect square, which will take away the square root. And then you should be able to work it out fairly easily. But I don't think that's not really the point of this procedure. In this case, just use Desmos. And if you don't mind, I will go to Desmos and do that with you guys. So let me bring up Desmos. You're going to get Desmos on the test, so you'll have access to it. So I'm going to I'm going to share. I'm going to go to Desmos. Um, so I'm going to type in int 1 to 2 square root 18 squared plus parentheses 18t squared plus parentheses 9 over t, close them up, squared, get out of the radical dt. And that's my answer. Done. I get 33.238, I guess, linear units. We'll say meters. How about that? Okay. Um, and that's it. Just do it that way. All right. Don't waste your time trying to work all this middle stuff out because really that's not that important. Okay. So um, use Desmos. I really want to emphasize that. The big picture thing is this. It's not so much that we care about how long arcs are. It's the relationship between two types of parameterization. The DT parameterization is the most common form, and this is what you generally have been doing since you started this class. And it's usually what I call the natural parameterization, like using sine and cosine for circles and stuff like that. The problem with DT parameterization is that it often subdivides the curve into uh, lengths of parts that are varying in length. So in other words, if I had a curve, it might divide it like that. You can see that the lengths aren't the same. And that's a problem sometimes. That's a DT parameterization. If I take that same curve and I do a DS parameterization, I'm actually dividing it into equal size subsegments. And later on, especially when we get to module 13, when we start doing line integrals, you want to traverse the path at a constant rate. You don't want to have your tangent vector being too long. And the way we kind of relate the two is through this formula here. We actually treat it as a basically a derivative of a integral, and you get ds dt is mag r prime t dt. And that's the relationship you need to know. This is important. Okay. Now, this may not be profound yet, while you're still just kind of learning this material. But when we get to uh, line integrals, it'll be really nice. Okay. So I'm more concerned that you can just get to this stage. You need to be able to set up the integral. Obviously, do the steps carefully. You need to get this part right. Don't forget your radical, your outside one. But then feed it into Desmos and let Desmos do the calculation for you. And so we had a question here. All of the 10-8 number 3 combos end up with a perfect square. Yeah, these are actually kind of artificial functions. Yeah, that's a good point. Each of these problems, if I go back to, let me reshare the screen. Yeah, each one of these three I'm sorry, the first three will work out to be perfect squares. But look how bizarre the functions are. These are really concocted up so that they do that. Equivalently, what if I just gave you something very basic? What if I just said, same problem, find the arc length of the parabola y equals x squared uh, from x equals 0 to x equals 2. All right, well your function would be t squared when you parameterize it. Your derivative would be 1 2t, and then when you do your mag of that, mag r prime, you get square root of 1 plus 4t squared. And then unfortunately, now you've got yourself a rough integral here. You've got 0 to 2 of rad 1 plus 4t squared. And that's going to give you your arc length. That's actually a correct integral. But this thing is rough because you're going to have to work it out using trig subs. And we don't do trig subs in this class. There's no point. So it's a concept that's easy to build. It's very easy to set these things up as long as you do the steps correct. It's a pretty easy process to get to the proper integral. But then most of the time the radical doesn't go away. You have to somehow deal with it, usually with, in this case, trig sub. But even sometimes it's impossible. If this was an x cubed, this would be 3t squared, t cubed, 3t squared. It'd be a 9t to the fourth. Forget it. You're not going to do it. There's no way to work out a quartic when it's caught underneath a radical. They just don't work out. You're going to those would have to be done numerically. So I don't want you guys to get too bogged down in the algebra here. You don't need to waste 20 minutes of your life working this out. Just get it set up, feed it into Desmos, get an answer. Okay? Don't waste your time. In fact, I think I'm going to make an announcement to the class on that because that's one way to. It's a time waster. All right. Uh, so there we are. Any questions on this one or related? This was the original question up here. All right, so 10.7, number 7. Consider the paraboloid z equals x squared plus y squared, period. Okay, fine. The plane 10x minus 10y plus z minus 6 equals 0 cuts the paraboloid, its intersection being a curve. Find the natural parameterization of the curve. And the words natural are quoted, because there's actually many ways you can parameterize it. So they're mainly looking for the what we would say the obvious one. All right, so let me write that information down. 10.7, number 7. We have a paraboloid z equals x squared plus y squared. We have a plane 10x take away 10y plus z minus 6 equals 0. Okay, so I'll stop the share there. So we're saying that these two things cross each other. So when two functions cross each other, um, yeah, you're going to substitute. Yeah, that's exactly what I was going with this. You're going to take this expression here and stick it in right there. So you're going to have um, 10x take away 10y plus x squared plus y squared take away 6 equals 0. Let's just kind of collect our terms here. We have x squared take away 10x plus 10x. Leave a little space plus y squared take away 10y. Leave a little space. And then minus 6 equals 0. In fact, I'll just leave it there. All right, um, so we're going to complete the square. We're trying to get these into a single squared binomial. So half of 10 is 5. Square of 5 is 25. I got to add it in to the other side. Half of negative 10 is negative 5. But then when I square it, I get plus 25 again. And then I can move the 6 over here. And so what do I get there? It's 56, I guess. Okay. So now it's the question, we got to parameterize this. And if you look at this, this is actually a circle. Okay. And it's centered at -5, +5 with a radius of rad 56. And so normally when you parameterize a circle, you go with cosine and sine. So we're gonna have to dress it up a little bit. Um, I want to get a radius of 56, so I'm going to put a rad 56 out. Let me think about that. Yeah, the radius is rad 56. Let me put a rad 56. I can always adjust this. And this will be cos t. And then I have to, so basically what I'm saying is x plus 5 is equal to this. Y take away 5 would be the sine. So rad 56 sine of t. So that tells me that x is going to be rad 56 cos t take away 5. Y is going to be rad 56 sine t plus 5. So that's the first two parts of the parameterization. I'm just kind of, I'm just double checking something here as I write. Oops, I didn't need that. Let me double check something here. So, yeah, that should work. All right. And then, so that takes care of the X and Y parameterization. And then you go back up to the Z, you might as well just go right up here, and because it'll be the same no matter what, because we set these equal to each other by substitution. Um, to get the Z parameterization, just take these two expressions and plug them into here. And so Z would be rad 56 cos t take away 5 quantity squared plus rad 56 sine t plus 5 quantity squared. And honestly, I would probably just leave it. You can FOIL this all out. It might clean up, In fact, it should clean up, but I'm not so sure you need to go through that hassle. I would just take the whole thing in this form and just blob it in there, and there you are. So you were correct that to start by substitution and complete the square, um, it's probably at this middle step where you have to kind of be, you have to first of all recognize what this is. It's a circle, um, centered at -5 + 5. So you basically you're going to force the parameterization, the usual cosine and sine parameterization, and we just dress it up. The radius goes out in front of as a multiplier out in front of the trig functions. So the radius is rad 56, and then we have these offsets. The x plus 5 is equal to this thing, so that means I can just subtract the 5 over and get that. And similarly, the y minus 5 is this part here, and I just add the 5. And so I get that. Um, okay, yeah, I see what you did. You missed. Yeah, you just didn't put them in, I guess. Okay. All right. And by the way, if you go into Desmos 3D, you should be able to play with this. I'm sure you can type it. You'd probably have to solve for Z though, but it should work out if you just want to see what it looks like. It's kind of fun to play with the 3D features. And again, you're going to have access to all of them. I'm going to give you access to the four main Desmos sites. The main site that you saw was called the just called Calculator. You'll be given access to the scientific calculator site, Matrix, and 3D. And you may not need all of them. In fact, I don't know if you'll need Matrix at all, but you'll have access to them. All right. Again, any clarification necessary on this one, I'd be happy to explain a step if you're wondering. Okay. Give me a second to get there. Share the screen here. Yeah, here we go. Find the velocity, acceleration, and speed of a particle with position function given here. Um, you're just taking derivatives. You have 9t sine t. That means you're going to have to do the product rule here. You're going to have to do the product rule for 9t cos t. This will just be a polynomial derivative. That'll give you your v. You're going to have to do the derivative again when you get to the a. So you're going to have to do the product rule probably a couple more times each time. This one, the third term, should just work out to be a linear, a constant value at that point. And then when you get to the v function, I'm sorry, when you get to the speed, which is magnitude of v, which is, by the way, is magnitude of r prime. Got done talking about that. Just take whatever values you get in these first three slots and magnitude them. And it will be ugly. It'll be a long, you'll have big radical and then parentheses, the derivative of 9t sine t squared inside a square. And oftentimes in cases like that, it may not be worth the trouble to FOIL it out, collect terms. You might want to just leave it the way it is, this massive radical with everything just kind of inside squares. So that's how I would do it. I wouldn't, you don't have to waste time with a lot of busy work algebra. Um, there we go. Go ahead and stop the share. Yeah, it should clean up. I guess since you're on an exam, there is a time uh, constraint. Sometimes it's probably not a bad thing to just leave it in its simplified form as long as you're careful with the syntax. So be careful when you're typing these things in. Make sure you close off your parentheses, for example. Make sure you're consistent with your variables. I've seen people type in T and then X, and that will actually get you a wrong answer, even if you have all the right elements. So be careful with that. Um, Kind of like when we were talking about arc length, you don't need to spend 20 minutes of your life working out the algebra because it just wants a number anyway. Yeah. Yeah, everybody's going to be, yeah, just go with what works for you. You know, some people are really handy with their algebra and don't mind foiling things out. But if you're feeling a little uncomfortable with that, or if you're under a time constraint, it should accept any equivalent. And by the way, and I'll announce this to everybody, I do check your wrong answers. So, uh, if I can tell that you had the right idea and your error was a syntax error, you'll probably get back some partial credit. That doesn't mean everybody will get back partial credit, but I do check everybody's wrong answers. If your answer is just plain wrong, you won't get partial credit. But if it was obvious you had the right idea and your finger slipped when you were typing, I usually grant back some partial credit. The Desmos calculator hotkey button gets blocked on my computer. That's weird. Um, what is the hotkey? Are you able to access Desmos? Oh, the square root. Oh, just type it in SQRT. So yeah, unfortunately, if a lot of these things, you just type in like int for integral and SQRT for square root. I think that's usually about it for this class. Um, just type in sine, cosine, tan for the trig functions. Yeah, we're aware of that. It's a frustrating thing. It doesn't happen to everybody. I'm not sure why. Sometimes just playing with your window size helps, but we've dealing with honor lock sometimes can be frustrating. So bear with me on this. Um, all right. Yeah, I'm sorry about that. Yeah, you can just type in the letters SQRT all in one. And that'll give you the square root symbol. So each one of these functions has a see you, Sam. Appreciate it. Um, each one of these things has I guess you could say a short letter equivalent. It's almost kind of like LaTeX if you've ever typed in LaTeX. They're very similar. Um, let's see what that one looks like. 10.9, number 8. A body of mass 10 kilograms moves in a counterclockwise circular path, radius 2 meters, making one revolution every 10 seconds. You may assume the circle's in the XY plane. All right, that one's not too bad. Let's do that one. 10.9, number 8. This will be our last one. So we need to figure out the centripetal force. Um, the kilograms doesn't really enter the mixture yet. The circular path has a radius of 2 meters, so that would be 2 cos and then something t, comma 2 sine and then something t, and we're making the revolution every 10 seconds. So what we want to do is you might remember from your days when you had the coefficient in front of there, the period is 2 pi divided by the b value. So it'd be divide the 10 here. So 2 pi over 10 is pi over 5. Now this is actually easy to check because if you put a 0 in, you're at cos 0 and sine 0. You're basically at 2, 0. And if you put in 10, well, you're at 2 pi, 2 pi. You've basically gone around the circle once. Okay, that's your position function. The magnitude of the force. Well, actually, that's your position function. We need to take some derivatives. So the velocity would be negative 2 pi fifths cos pi fifths t. This would be 2 pi fifths cos. Oh, my bad, that's a sine here, my bad. And this will be a cos pi fifths t. And then the acceleration would be the derivative of that. Oh boy, so we're going to get negative 2 pi squared 25ths cos pi fifths t. This will be a negative 2 pi squared 25ths sine pi fifths t. And that's your acceleration. And then once the force, so this is where you just pull up that old famous formula from physics. You just multiply the whole thing by 10. So that's where the 10 kilograms comes in. You've got your acceleration right here. So you can feed the 10 through as a multiplier or leave it on the outside. All right. Well, I'm going to go ahead and power down here. And so the test starts at 4 p.m. Arizona time. You make sure that you figure out what the time difference where you are. Arizona does not do daylight savings. So most of the rest of the United States is on daylight savings right now. Um, but we are not. So we're actually aligned with the West Coast right now. For example, we're at the same time as LA, and we're 3 hours behind the East Coast. But you guys just make sure that you don't make that simple error when you're figuring out the time difference. And I'll make a couple of announcements in Canvas here regarding some stuff I talked about today. All right. Well, good luck, and I'll be monitoring over the next couple of days. 5, 4, 3, 2, 1, bye.